Hello again. In the second set of slides devoted to global spatial autocorrelation, I will talk about something that is maybe a little unusual. The Geary and Moran's tests are classic fare in every spatial analysis book, but the visualization of global spatial autocorrelation actually provides the beginning of a transition to the treatment of local spatial autocorrelation. And I'll talk about three different devices as I refer to them. One is the Moran scatter plot, which I believe is the most useful of the three because it makes a direct connection between global and local. And then two other visualizations that are based on a different view of measuring spatial autocorrelation and specifically relating the strength of the autocorrelation to distance decay. So the Moran scatter plot, just to recap, Moran's I, here's the expression. Numerator, we have the cross products, we have the weights matrix, we have the sum of all the weights as the scaling factor, and in the denominator we have the variance. So the z's are in deviations from the mean. As I mentioned a couple of times already, when we have row standardized weights, that means the weights in each row of the matrix sum to 1. Then the sum, this S naught, the sum of all the weights, equals the number of observations, n. That is, if there are no isolates. But the typical case, that is n. And in that case, these scaling factors, the S naught in the numerator and the n in the denominator, cancel each other out. So then we're left with this simplified expression. Again, in the numerator, we have the cross product, we have the weights, and then we have the variance in the denominator. Now, with a little bit of manipulation, what we can do is we can move zi out of this because the sum is over zi. So for every I, this zi will be the same. More specifically, let's say we look at the first observation. So I would be 1. Then what is the second part? That's the sum over all the neighbors, the W1J that are not 0, of the product of Z1 with the value at that neighbor. So the Z1 is always the same. We move it out of this operation. So we end up with this expression. And this expression, to refresh your memory, if you know the formula for the regression coefficient in a bivariate regression, you may recall that's the sum of the cross products of x and y in the numerator, and then the sum of the squares of x in the denominator. So looking at this from that perspective, what we see here is in fact that this ratio, which is Moran's I, is nothing but a slope of a bivariate regression where the dependent variable, and this is a little counterintuitive, but it makes sense mathematically, the dependent variable is this term. And I alluded to this a little bit when we talked about spatial weights. This sum, or really a weighted average of the neighbors, we call a spatially lagged variable or a spatial lag variable. So in other words, Moran's I is the number that we get for Moran's I is the slope in a bivariate regression line of the variable at each location regressed upon its spatial lag, the average of the values at the neighboring locations. And that's the critical point, because now we can connect the Moran's I, which is a pretty abstract, formula, this equation here, to a visual representation, and we can find out what contribution each location makes to this global statistic. And more importantly, we can start distinguishing different types of spatial autocorrelation, which is the first step, as I mentioned, towards thinking about it in terms of local spatial autocorrelation, or LISA. So what does this scatter plot amount to? It is simply a scatter plot of the values standardized on the x-axis, and on the y-axis we have the spatial lag. So this is not what you think of those of you who may have done some time series regression may think of a autoregressive model where you regress the observation at some time on the past, or here it would be at a location on its neighbors. In fact, it's the reverse. It's flipped around. So the dependent variable is the average of the neighbors. The explanatory variable, the x variable, is the value itself. So we just plot these points, these pairs of points, and then we do a linear fit through the scatter plot. The slope of that line is Moran's xi. And we continue to use this example of house prices for Cleveland, for a subset of Cleveland transactions. And you see they bunch a lot together. There's quite a few observations here. But as we fit the line through them, the slope of the line is Moran's xi. And importantly, we see, or we can assess more formally, this is just a visual identification here, these outlying values. And these are, so this is the x-axis, actually, this is the x-axis in standardized, so these are in units, standard deviational units. These variables, this rent, is something like 8 or 9 standard deviational units above the mean. This is the mean, right? So this is something that we could think of as being an outlier. Maybe this is a multi-million mansion that sold, and it, because of its relationship to its neighbors, these are the neighbors, this is the average of the neighbors, this is the rent itself, it actually pulls this line down. And so we can investigate this scatter plot. In fact, when I developed this was my original motivation, is to look at the sensitivity of the global Moran's xi to potential high leverage observations. These are potential observations that exert more influence on the slope of the line than they should. And so these are the kinds of points you want to identify in function of possibly being spatial outliers, possibly suggesting spatial heterogeneity, and so on. The scatter plot itself is as simple as it can be. On the x-axis, the values that we observe at each location in standard deviational units, and on the y-axis, the spatial lag that corresponds with that. In other words, the average value at the neighboring locations. So the main purpose of the Moran scatter plot, other than assessing the sensitivity of the global Moran's xi to its particular observations, is to start thinking about different categories of spatial autocorrelation. And we do this by looking at the scatter plot and distinguishing 4 quadrants centered on the mean. So it's very important that we keep in mind that this is centered on the mean. Everything we say in terms of high or low is high or low relative to the mean. That mean itself may be very low. That's not taken into account. It's a relative measure relative to the mean of the variable. So we have 4 quadrants. 2 of these correspond with positive spatial autocorrelation, and 2 of these correspond with negative spatial autocorrelation. And as we've seen in the previous module, positive spatial autocorrelation is when we find clusters of like values or locations are similar to their neighbors. Similar, not high, not low, similar. And we'll see in a second how we distinguish between high and low in the Moran scatter plot. Then the other 2 quadrants show the opposite. They show that the values at a location are very different from their neighbors. So you have relatively high values surrounded by neighbors, or more precisely, the average of the neighbors that is lower, or the other way around, which I call a spatial outlier, and which is evidence of negative spatial autocorrelation. So let's go back to our scatter plot and investigate these 4 quadrants a little more closely. So we have our four segments, so to speak. In this one on the left, these points are all above the mean. So they're on the right side of the mean, and their neighbors are also above the mean. And I refer to this as high positive spatial autocorrelation. So it's positive spatial autocorrelation because the observations are similar to their neighbors, and it's high because it pertains to observations that are above the mean and neighbors that are also above the mean. Okay, on the right, we are below the mean for the observations, and the neighbors are also below the mean. So this is still positive spatial autocorrelation because it's similar, but it's of the low kind. So this is two types of positive spatial autocorrelation: high values surrounded by high, and then low values surrounded by low. And when we focus on local spatial autocorrelation, we'll be able to pick out exactly which of these values that are high or low are significant. That's the topic of the next module. But very importantly, right away, when we construct this Moran scatter plot, we can divvy up the nature of spatial autocorrelation into positive and negative, and among the positives, we can make the distinction between high and low. And then we move to the off-diagonal segments. Here we have on the left observations that are above the mean, surrounded by the average of the neighbors that's below the mean. So I call this high-low, and I call this a spatial outlier, dissimilar from the neighbors, so negative spatial autocorrelation, high-low. And then this last situation is the opposite. We have the x variable is below the mean, is low, and it's surrounded by neighbors, the average of which is above the mean, so high. So this is a low-high negative spatial autocorrelation. So to recap, by means of this very simple graphic, we not only have the value of Moran's I as the slope of the line, but we can start distinguishing between four types of spatial autocorrelation: two positive ones, high, low, and two negative ones, high-low and low-high. And we'll revisit that when we focus on local spatial autocorrelation. Now, what else can we do with this Moran scatter plot? So we can, obviously, the slope is Moran's I. We can assess the sensitivity of that slope to high leverage observations. We can distinguish between four types of spatial autocorrelation. And then finally, we can also look for structural breaks, and always our same focus on potential structural breaks that might be spatially driven, suggesting spatial heterogeneity. So to that effect, one thing we can do is we can use a local regression smoother, the same we've already seen before, as a nonlinear smoother to see if there might be some potential structural breaks in the following sense. Are there subregions in the data that show different spatial autocorrelation from other subregions that would be manifested by a different slope in the lowest curve? So here's an example, again, for our Cleveland data. And in essence, we see that this slope is actually pretty good up to this point. And then we start seeing problems that, in the sense that this slope, for all the observations that are to the right of here, is all of a sudden much flatter and even somewhat negative to some extent. So what we would then do in practice is select these observations and see how they stack up in our other views of the data. Remember, it's all in the spirit of dynamic graphics, interactive linking and brushing. So we try to make connections between patterns that we see in one graph and patterns that we might see in another graph. So that's the third use, or if you wish, the fourth use of the Moran scatter plot. So it's a very simple device. It's a scatter plot with a linear fit of the observations against the average of the neighbors. The linear fit is Moran xi. You can look at high leverage observations that affect the slope. We can distinguish between 4 different types of spatial autocorrelation, and we can assess structural stability in the Moran xi. So a lot of things we can look at in terms of what is building up, what is behind the scenes in terms of coming up with this single statistic of Moran xi. So the Moran xi is based on a cross-product statistic, and it uses spatial weights. There is quite a sentiment that these spatial weights are somewhat too constraining, but really, there isn't really a solution. As we saw the other week, is the weights are there because our cross-sectional data are insufficient to give us full information on the interactions that we're interested in. But there is a different perspective, and that perspective brings Tobler's law in directly and relates the strength of the correlation to the distance, the distance decay, to the distance that 2 observations are from each other. Remember, both in Moran xi as in Geary C, we're always talking about pairs of observations. In Moran xi, we take the product. In Geary C, we take the square difference. So here we have a non-parametric perspective. This is not as commonly used, but I think it can be quite insightful in that there is no model. There is no, the data drive the functional form. So basically what we have is a bunch of data. We compute, in essence, cross products for every possible pair, and then we plot the value of that cross product against the distance that separates the 2 points in the pair. So the product is an estimate for the covariance function, the auto covariance, because again, it pertains to the same variable. And we take this kind of non-parametric kernel smoothing, local regression smoothing perspective to this phenomenon. In principle, we have a spatial autocorrelation between locations I and j as a function, obviously, of the values of z at I and j. And we compute this in practice. We standardize the variable so that the variances are 1. They're all centered on 0, so we don't have to worry about the denominator. We just take the product of the 2 standardized variables. Now, to fit a functional form to this, we already saw we have to put some structure into this process, because these parameters, the number of such parameters, these are essentially interaction parameters. We talked about this in the context of spatial weights. So these interaction parameters, their number of them increases with the square of the number of observations. So we can't win this battle. So what we do then instead is we take a non-parametric approach, as I mentioned, and express that autocorrelation coefficient as an unspecified function of distance. More formally, we say that this autocorrelation between location I and j is some unspecified function g of the distance between I and j. And we're basically going to throw all these points in a graph where we have the cross product on the y-axis and the distance on the x-axis, and fit a curve through it. And what kind of curve? A local regression or a kernel function. So in essence, this is a non-parametric, nonlinear smoothing of a scatter plot, very much in the same way that we did a lowest smoothing of our standard scatter plot or of the Moran scatter plot. In this case, the scatter plot pertains to the cross products on the one axis and the distance on the other axis. With the Moran scatter plot, the actual observations are on the x-axis and the neighbors are on the y-axis. So there's a different way of looking at the spatial interaction. So the local regression, you can get different results depending on the kind of smoother that you use. And the upshot of it is that you get a curve that shows how the strength of the spatial autocorrelation varies with increasing distance. And recall Tobler's law. Tobler's law suggests that the strength of this correlation should decrease with increasing distance. And because we don't force a function that guarantees that. Remember when we talked about the distance weights, we said our weights matrix has to be such that distance decay is respected. So we use inverse distance or a negative exponential function of distance. But here we don't specify any function at all. It could be anything the data suggests it is. So we could end up with segments in this curve, in this function, that actually increase with distance and thereby violate Tobler's law. That is just something that you get when you let the data play freely. Now, what does this mean? Does that mean Tobler's law is wrong? Well, not necessarily. What it means is that there's other factors in play that complicate the picture. Maybe the distance in question is not the proper distance to measure separation or interaction. Maybe the interaction works through other networks than geographical distance. And so by and large, we can have a long discussion about this, but by and large, Tobler's law is basically an empirical reality, although it doesn't apply in 100% of the cases. So let's see what this looks like in GeoDa. In GeoDa, we implement this with a lowest type of regression. And so what we do is we bin the observations because there's so many, everything is a square of the number of observations. So if you have a few thousand observations, you very quickly have enormous number of points in this scatter plot. So the histogram bars show you how many observations are in the bin, and then we smooth the points for the bins. And in this particular example, it shows a distance decay up to a point where it crosses the zero line. And one interpretation of this correlogram is that this is the range of interaction. This is how far the interaction works. And beyond this, we basically get noise. In fact, you could argue it goes up a bit here, but essentially it's flat, meaning there is no effect of distance of separation on the correlation between those pairs of locations. They are too far apart for the interaction to be effective. Now, one problem with this kind of graph, and it's a similar problem that we encounter in geostatistics. Now, geostatistics would be a whole other course or even a whole year in its own right, and I purposely leave it out. It's really more appropriate in the natural sciences, but in geostatistics, a lot of emphasis is given on the relationship between a measure of dissimilarity and the distance in the covariogram, and it's called a covariogram in geostatistics. And every variogram or covariogram has a counterpart as a correlogram. Now, this correlogram is not quite the same because it's non-parametric. In geostatistics, you tend to use specific functions for this, but it's in the same spirit in that you also can find a range of interaction. One problem with this, and you see this on the right-hand side of the curve, is that as the distances become larger and larger, the number of pairs of observations that fall into these bins decreases tremendously. And this, one could argue, and we could also demonstrate, can exert undue influence on the shape of the curve. It's like high leverage points. You don't want them there. So typically, what we do is we reduce the distance for which we consider pairs. And you see here, pretty much everywhere, there is a nice chunk of observations. You can see here how many there are. Rule of thumb is to have at least 30. So here we have a little more precise view of what goes on, and we have a fairly flat curve up until this kind of distance, about 5,000 feet. And then we have a steep decline where it crosses around here, around 6,000 some feet. It crosses the zero line. So this again gives us a measure of the range of interaction. Beyond here, the interaction is actually negative. The spatial interaction, because this measure on the y-axis is a measure of covariance or autocorrelation, really. So once you hit the zero line, you have negative spatial autocorrelation. And then if you go far enough, you go back and you get positive again. So these areas, once you hit the zero line, are really not that insightful and not very meaningful unless you do some very formal modeling, which we don't get into. So the main point of the correlogram is to provide a non-parametric perspective that does not force a particular functional form on how the spatial autocorrelation changes with the distance that separates the pairs of observations. So some people see it as an alternative to specifying spatial weights, but there's no free lunch, because we do not have the full interaction data. We have to resort to some function of distance, and that function may or may not be appropriate depending on the data. And then the last form of visualization is something that we developed just very recently. It provides yet another way of thinking about this. And again, it's based on a scatter plot where on the one axis we have geographical similarity, again the distance, the same distance we just had. But on the vertical axis we don't have a covariance, but we have a distance in attribute space. And this distance in attribute space, I'll revisit in the last module when I talk about multivariate spatial autocorrelation. This is a way to move, a fairly straightforward way to move from one to higher dimensions. Because, so everybody knows this Euclidean distance equation where you have the difference in the x-axis, the difference in the y-axis squared, and then the square root of this. This is a measure of distance. You can make this completely general in that x here are coordinates, but they could also be the values for a given variable, zk, at location I and at location j. So we take the square difference, and we can have as many variables as we want, and then at the end we take the square root out of this sum, and that is a measure of distance in attribute space. If you recall our 3D data cube, we had those points floating in three-dimensional space. We could construct a measure of distance between those points in multi-attribute space. That's exactly what this is. So the idea then of this distance scatter plot is to plot the distance in attribute space against the distance in geographical space. And obviously what we would expect is that the distance in attribute space, because there's a dissimilarity, increases with the distance in geographical space. That is what Tobler's law would suggest. And so this smooth distance scatter plot, which is a very simple device, gives us a sense of how the attribute dissimilarity stacks up against geographical distance. And because there's too many points, just like in the previous one, we smooth the scatter plot, and that brings out an overall pattern. And just to show you what this looks like, this is an example, and we'll use this example quite a bit once we move to local spatial autocorrelation. This is a historical data set with socioeconomic data for France in 1830, and we'll be using this data, the Gary data set. And these are just 6 variables, different kinds of crimes, suicides, literacy, and so on, plotted with, on the horizontal axis, distance in kilometers, and on the vertical axis, distance in attribute space. And so the general pattern is that this increases over a range and then flattens out and might even decrease. When you have things like this is literacy, that suggests a high degree of homogeneity in the data. So not a lot of variance, because even after such a large distance of separation, there is still a slope in this. So remember, Stobler's law has, in this case, the dissimilarity increasing with distance, but at some point it should flatten out. Now the real motivation for developing this graph and for using it is to move to multivariate spatial autocorrelation, which is, as it turns out, is very hard to do with Moran's eye, but a lot easier to do with Geary-C. And here we see this curve, this smooth curve for 3 variables taken together. So the distance in on the variable distance axis is a distance in 3-dimensional multi-attribute space, and the horizontal distance is geographical distance. So here we see what we want to see, basically. This is Stobler law perfectly executed. Increase with distance up to a certain point, beyond which it flattens out, beyond which there is no more spatial interaction. And then, because the attribute distance in the attribute distance is simply summing more square differences, it's easy to generalize. This is for all 6 variables, and we see again the same general shape where we go up to a point and then it flattens out. So what we've done here in this module is tackle specific measures of global autocorrelation. We've looked at Moran's eye, we've looked at Geary-C, we've looked at inference, and then we move to visualizing these spatial autocorrelation measures. And the Moran scatter plot turns out to be, at least I think so, very useful device to not only compute Moran's eye, but also assess its sensitivity to high leverage points, distinguish between 4 different types of spatial autocorrelation, and potentially assess structural breaks. The 2 other plots are more interesting in terms of assessing the range of interaction. In the correlogram, we use as the y-axis the cross product of the standardized variables, and in the smooth distance scatter plot, we use on the y-axis the distance in attribute space, and both of these have the distance, just geographical distance, on the x-axis. The correlogram is supposed to go down with increasing distance. The distance scatter plot goes up with increasing distance, and the range of interaction is the point where both of these curves flatten out. So this concludes the discussion of global spatial autocorrelation. The next module will tackle local spatial autocorrelation.